Session policy versus permission boundary versus trust policy versus resource policy. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Session policies, permission boundaries, trust policies, and resource policies are four distinct IAM mechanisms that are often confused because they all involve restricting or controlling permissions. However, they operate at different stages of the authorization process, have different purposes, use different logic models, and are applied in different contexts. Understanding when and how each one is used is critical for implementing proper IAM governance in AWS. Let's start by examining the first flowchart diagram, which shows the trust policy flow. Trust policies control who can assume a role in the first place. At the top, we have the principal node representing any entity that wants to assume a role, such as a user, another role, or an AWS service. An arrow flows from principal to a decision diamond labeled role. Trust policy allows principal. This is the first gate that must be passed. The trust policy is attached to the IAM role itself and specifies which principals are allowed to assume it. The trust policy is evaluated by a AWS security token service when an assume role request is made. If the trust policy does not allow the principal, the check returns no, and the flow proceeds to a red node labeled access denied, cannot assume role. The role assumption fails immediately, and the principal never receives credentials. This is the trust policy's primary function: to act as a gatekeeper preventing unauthorized entities from even attempting to use the role's permissions. If the trust policy allows the principal and the check returns yes, the flow proceeds to a green node labeled assume role success and principal gets credentials. The principal receives temporary security credentials including an access key, secret key, and session token that can be used to make AWS API calls with the role's permissions. The key point illustrated by this diagram is that trust policies are evaluated before any permissions are considered. They answer the question who can assume this role, not what can they do with it. Trust policies use the principal element to specify allowed entities, and they are resource-based policies attached to the role itself. Without a trust policy that allows you cannot assume the role regardless of what permissions you have. Now let's examine the sequence diagram for trust policies, which shows the detailed interaction during role assumption. The diagram has four participants. First is principal, representing either a user or an AWS service that wants to assume a role. Second is AWS STS, the security token service, which handles role assumption operations. Third is IAM role, representing the role being assumed. Fourth is trust policy, representing the trust policy document attached to the role. The sequence begins with principal sending an assume role request to AWS STS. This is typically done using the STS:\assume role API call, specifying the ARN of the role to assume. STS then sends a message to IAM role labeled retrieve role details, asking for the role configuration including its trust policy. IAM role forwards a message to trust policy labeled check trust policy, requesting evaluation of whether this principal is allowed. Trust policy then evaluates the principal by checking if the principal's ARN or service identifier matches any of the principals listed in the trust policy document, shown by the self-referencing arrow labeled evaluate principal. At this point, the diagram shows an alt box with two paths. In the success path labeled principal allowed in trust policy, the trust policy sends a response back to IAM role labeled principal authorized, indicating the trust check passed. IAM role then sends a message to STS labeled generate credentials, instructing STS to create temporary credentials. STS responds to principal with return temporary credentials including the access key, secret, and session token. The principal can now use these credentials to make API calls with the role's permissions. In the failure path labeled principal not in trust policy, the trust policy sends a different response to IAM role labeled principal denied. IAM role then sends a message to STS labeled trust policy violation, indicating the assumption was not authorized. STS responds to principal with an error message labeled error access denied cannot assume role. The role assumption fails completely, and no credentials are issued. The note at the bottom emphasizes that the trust policy is the gatekeeper for role assumption, the first barrier that must be passed. Now let's examine the second flowchart diagram, which shows the permission boundary flow. Permission boundaries control the maximum permissions an IAM user or role can have. At the top, we have the IAM user or role node representing an identity that has both identity-based policies and a permission boundary attached. An arrow flows to a box labeled Identity Policy grants permissions representing the standard IAM policies that grant permissions to perform actions. From there, an arrow flows to a decision diamond labeled Permission Boundary allows action. This is where the critical intersection happens. Even if the identity policy grants a permission, the permission boundary must also allow it for the action to succeed. If the permission boundary does not allow the action, the check returns no, and the flow proceeds to a red node labeled Action Denied Boundary Restriction. The action is blocked even though the identity policy would have allowed it. Permission boundaries can only restrict permissions, never grant them. If the permission boundary allows the action and the check returns yes, the flow proceeds to a box labeled Effective Permission Granted, which is the intersection of identity policy and boundary. The action is allowed because both the identity policy grants it and the boundary permits it. The note at the bottom of this diagram emphasizes that permission boundaries set maximum permissions. They define the outer limits of what an identity can do, regardless of what identity policies grant. This is particularly useful for delegated administration where you want to give someone the ability to create users or roles, but ensure those users or roles cannot exceed certain permission limits. Now let's examine the sequence diagram for permission boundaries, which shows how they are evaluated during a PI requests. The diagram has 5 participants. First is IAM user with boundary, representing a user that has a permission boundary attached. Second is AWS service, for example S3, representing the service receiving the API request. Third is IAM authorization, representing AWS's authorization system. Fourth is identity policy, representing the user's attached policies. Fifth is permission boundary, representing the boundary policy. The sequence begins with IAM user sending an API request to AWS service. For example S3 put object to write an object to S3. AWS service immediately sends a message to IAM authorization labeled authorize request, asking whether this user is allowed to perform this action. IAM authorization sends a message to identity policy labeled check identity policies, requesting evaluation of the user's attached policies. Identity policy responds back with action allowed in policy, indicating the identity-based policies grant this permission. However, IAM authorization is not done yet. It sends another message to permission boundary labeled check permission boundary. Permission boundary evaluates whether the action is within the allowed maximum permissions, shown by the self-referencing arrow labeled evaluate action against boundary. The diagram then shows an alternate box with 2 paths. In the success path labeled action allowed in boundary, permission boundary responds to IAM authorization with boundary permits action. IAM authorization then performs the intersection calculation shown by the self-referencing arrow labeled calculate effective permission identity policy intersection boundary. Since both the identity policy and boundary allow the action, IAM authorization sends authorization granted back to AWS service. AWS service then responds to IAM user with request successful. In the failure path labeled action not in boundary, permission boundary responds with boundary blocks action. Even though the identity policy allowed the action, the boundary restriction overrides it. IAM authorization sends authorization denied to AWS service, and AWS service responds to IAM user with error access denied boundary restriction. The note at the bottom emphasizes that the boundary creates a maximum permission envelope that cannot be exceeded. Now let's examine the third flowchart diagram, which shows the session policy flow. Session policies are optional inline policies that can be passed during an assume role operation to further restrict the permissions of the resulting session. At the top, we have the role assumed node representing a role that has been successfully assumed by a principal. The role has a base set of permissions defined by its permission policies. An arrow flows to a decision diamond labeled session policy provided. This check determines whether a session policy was included in the assume role request. Session policies are optional, so if no session policy was provided, the check returns no, and the flow proceeds to a green node labeled full role permissions apply. The session has all the permissions that the role's policies grant. However, if a session policy was provided and the check returns yes, the flow proceeds to a box labeled calculate effective permissions as role policy and sign session policy. This is the intersection calculation. The effective permissions are limited to only those actions that are allowed by both the role's permission policies and the session policy. From there, an arrow flows to a green node labeled restricted session permissions apply. The session has fewer permissions than the role normally provides because the session policy has restricted them. The note at the bottom of this diagram emphasizes that session policies can only restrict, not expand, permissions. They are useful for temporary delegation scenarios where you want to grant someone limited access to a role without changing the role's base policies. Now let's examine the sequence diagram for session policies, which shows the complete flow from role assumption through API requests. The diagram has 5 participants. First is user, representing someone assuming a role. Second is AWS STS, handling the role assumption. Third is IAM role, representing the role being assumed. Fourth is session policy, representing the optional inline policy. Fifth is AWS service, for example DynamoDB, representing the service being accessed. The sequence begins with user sending an assume role request to AWS STS, specifying an optional session policy. STS sends a message to IAM role labeled validate trust policy to check if the user is allowed to assume the role. IAM role responds with trust check passed, confirming the user is authorized. The diagram then shows an alt box with 2 paths based on whether a session policy was provided. In the session policy provided path, STS sends a message to session policy labeled apply session policy. Session policy performs the intersection calculation shown by the self-referencing arrow labeled calculate effective permissions role policy intersection session policy. Session policy responds to STS with restricted permissions. STS then returns credentials to user labeled credentials with limited permissions. When the user makes an API request using these session credentials to AWS service, the service evaluates the request shown by the self-referencing arrow evaluate against session restricted permissions. AWS service responds with action allowed or denied based on session policy, where the authorization is based on the restricted permissions, not the full role permissions. In the no session policy path, STS directly returns credentials to user labeled credentials with full role permissions. When the user makes an API request to AWS service, the service evaluates against the full role permissions shown by evaluate against full role permissions. AWS service responds with action allowed or denied based on role policy. The note at the bottom emphasizes that session policy restricts for this session only. It does not modify the role's base policies and does not affect other sessions using the same role. Now let's examine the fourth flowchart diagram, which shows the resource policy flow. Resource policies are fundamentally different from the other 3 because they are attached to resources like S3 buckets, SQS queues, or KMS keys, rather than to identities or roles. Resource policies control who can access the resource and use union logic rather than intersection logic. At the top, we have the principal requests resource access node representing any principal attempting to access a resource. An arrow flows to a decision diamond labeled identity-based policy allows. This checks whether the principal's own identity-based policies grant permission to access the resource. If the identity policy allows the action, the check returns yes, and the flow proceeds to another decision diamond labeled resource policy allows. If the identity policy does not allow the action, the check returns no, but the flow still proceeds to the resource policy allows diamond. This is crucial. Unlike permission boundaries which require both to allow, resource policies use union logic where either the identity policy or the resource policy can grant access. At the resource policy allows diamond, AWS evaluates whether the resource policy attached to the resource explicitly allows this principal to perform this action. If the resource policy does not allow it, the check returns no, and the flow proceeds to a red node labeled access denied. However, if the resource policy allows it, the check returns yes, and the flow proceeds to a green node labeled access granted identity or resource policy. The key word is OR, meaning access is granted if either the identity policy or the resource policy allows it. The note at the bottom emphasizes that resource policies can grant cross-account access, which is their most powerful feature. Now let's examine the sequence diagram for resource policies, which shows cross-account access scenarios. The diagram has 5 participants. First is principal from account A, representing a user or role in one AWS account. Second is AWS resource, for example, an S3 bucket in account B, representing a resource in a different account. Third is IAM authorization, representing the authorization engine. Fourth is identity policy, representing the principal's policies in account A. Fifth is resource policy, representing the bucket policy in account B. The sequence begins with principal sending an API request to the resource, for example, S3:get object to retrieve an object. The resource forwards this to IAM authorization labeled authorize request. IAM authorization first checks the principal's own policies by sending check principal identity policies to identity policy. Identity policy responds back with policy result, which might be allow, deny, or no explicit statement. IAM authorization then sends check resource policy to resource policy. Resource policy evaluates the principal's ARN against the policy statements, shown by the self-referencing arrow labeled Evaluate Principal ARN. The diagram then shows an alt box with 2 paths. In the success path labeled Identity Policy allows or Resource Policy allows. Resource Policy responds with access granted. The note box shows union logic allow if either permits. This is the key difference from permission boundaries. IAM authorization sends authorization successful to resource, and resource responds to principal with request successful return data. In the failure path labeled both deny or no explicit allow, resource policy responds with access denied. IAM authorization sends authorization failed to resource, and resource responds to principal with error access denied. The note at the bottom emphasizes that resource policies enable cross-account access, allowing principals from other accounts to access resources without requiring role assumption in the resource's account. Now let's look at the sequence diagram which shows how all 3 mechanisms work together in a complete flow. The diagram has 5 participants. First is user representing an IAM user who wants to perform an action. Second is identity policy representing the user's attached policies. Third is permission boundary representing the boundary policy attached to the user. Fourth is target role representing the IAM role the user wants to assume. Fifth is session policy representing an optional inline policy for the session. The sequence begins with user sending a message to identity policy labeled check action permission. The identity policy evaluates whether the user's attached policies grant the requested action. If the user has a permission boundary, identity policy sends a message to permission boundary labeled Apply Boundary Filter. The permission boundary responds back to identity policy with effective permission calculated as the intersection. Identity policy then sends a response back to user labeled Action Allowed or Denied. If the action is to assume a role, the flow continues. User sends a message to target role labeled Assume Role Request. The target role evaluates its trust policy to determine if this user is allowed to assume it. If the trust policy permits the user, the flow continues. If the Assume Role request includes a session policy, target role sends a message to session policy labeled Apply Session Restriction. Session policy responds back to target role with restricted credentials. Finally, target role sends a response back to user labeled Return Credentials with effective permissions. These credentials have permissions that are the intersection of the role's base permissions and any session policy that was applied. The note at the bottom of the sequence diagram summarizes the evaluation order. First, trust policy for role assumption. Then permission boundary for user actions. And finally, session policy for session restrictions. Each operates at a different stage and serves a different purpose. Now let's examine the comparison table on the slide, which summarizes the key differences. The table has 5 columns: policy type, purpose, when evaluated, attached to, and can grant permissions. The first row shows trust policy with purpose controls who can assume a role, evaluated during assume role, attached to IAM role, and it specifies principles allowed not traditional allow deny on actions. The second row shows permission boundary with purpose sets maximum permissions, evaluated during all API calls, attached to IAM user or role, and no it only restricts. The third row shows session policy with purpose restricts session permissions, evaluated during assume role when provided, attached to role session as inline, and no it only restricts. This table clearly shows that trust policies are fundamentally different from the other two because they control role assumption rather than action authorization. Permission boundaries and session policies are similar in that they both restrict permissions, but they differ in when and how they are applied. Permission boundaries are permanently attached to an identity and affect all actions that identity attempts. Session policies are temporary and only affect a specific role session. The code example at the bottom shows all 4 mechanisms in one scenario. The first block is a trust policy on a role, allowing a specific IAM user to assume it. The principal field specifies the user ARN, and the action is STS:"assume role." The second block is a permission boundary limiting a user to only development resources using tag-based conditions. The condition block uses string equals to check that resources have an environment tag with value development. The third block is a session policy further restricting to read-only S3 operations. The action field only includes S3:getObject and S3:list bucket, and the resource field limits access to a specific bucket named dev data bucket. The fourth block shows a resource policy, specifically an S3 bucket policy, that allows cross-account access. The policy has version set to 2012-10-17 and a statement array. The effect is allow, and the principal field specifies AWS with the value ARN:AWS:"IAM:"account number:"root, which represents the entire account number. This allows any principal in that account to potentially access the bucket. The action field includes S3:getObject and S3:putObject, allowing both read and write operations. The resource field is ARN:AWS:"S3::shared bucket/*, matching all objects in the shared bucket. This resource policy enables cross-account access without requiring users in account number to assume a role in the bucket's account. They can access the bucket directly using their own credentials, as long as the resource policy allows it and their own identity policies also allow it. When all 4 mechanisms work together, the authorization logic is complex but predictable. For role assumption, the trust policy must allow the principal. For actions by identities with permission boundaries, both the identity policy and the boundary must allow the action using intersection logic. For role sessions with session policies, both the role policy and the session policy must allow the action using intersection logic. For resource access, either the identity policy or the resource policy can allow the action using union logic. All four mechanisms work together to create layered, flexible security controls. Thank you for your attendance. Please consider subscribing to the channel and liking this video.